It gives me great pleasure to welcome to this meeting Professor Elia Merzari from Penn State University, and thank him very much for agreeing to give this very interesting presentation, but also for agreeing to give this presentation at what must be a very awkward time for him this time of the night in the United States. The presentation will be, the keynote invited presentation will be towards full Core CFD, some recent updates from NEAMS and ExaSMR programs. So without any further delay, I will hand over to Professor Merzari to start his presentation.
Thank you very much for the introduction and for the opportunity to speak here. So first, let me tell you that this is the work of many people. It's not just mine, but I want to, I'm not going to name them all, but there's a not complete list there, an incomplete list there. So what I'm going to talk today is our efforts to scale toward larger and larger cases. It's not everything we are doing. So a lot of the effort in the NEAMS and ExaSMR programs, which probably you've not heard, but I'm going to briefly mention what they are also toward Core CFD, toward improving system analysis, and through a full layer of multi-scale thermal hydraulics. However, what I'm going to talk primarily today is not full Core CFD in that sense, but rather an effort to scale more and more large eddy simulation and to reach the and RAMS methods to reach the point where we can simulate a full core. So the ExaSMR program is really an exascale project. It's tied to the ECP program, which is the exascale computing program. And NEAMS is a longer running program that is actually tied more to the nuclear energy needs. The exascale program covers a broad range of topics. So this is just a slide to show some of the things we have been doing in the past 10 years. So nowadays, 1 billion degrees of freedom is becoming relatively common. And with 1 billion degrees of freedom, there's a lot of things you can do. You can do parts of a fuel assembly. You can do helical coil, parts of a helical coil steam generator, like in this case. You can do parts of a pebble bed, or parts of an assembly of MSR design. So there are, with this range of degrees of freedom on petascale system, this is not unusual to see this nowadays. So today, what we're going to really talk about is how we can scale this up to larger and larger system on pre-exascale systems. And I'm going to introduce our new code, which is an evolution of NEC 5000, which is really breaking our records on what is possible to do nowadays. And I would say that while it is primarily aimed at exascale, a pre-exascale system like Summit, it is actually outperforming NEC 5000 even on the CPUs today. So, but first, a little bit of on NEC 5000, which I'm way already mentioned, but in case you have not, you're not familiar with the code, it is essentially a spectral element code. We use it it's really the main CFD tool under the NEAMS and ExaSMR programs. We have integrated, it's open source, so we have integrated with many other codes. It has a MOOS interface, and MOOS is like flexible framework, not that different from DL2 from the European framework that is popular nowadays too. And it allows to do a lot of other physics, and this interface is an important item for us. It has a range of fidelity. It is primarily used for DNS and LES. However, we have added over the years a few Reynolds average Navier-Stokes models and even some porous media models. But primarily, there are limitations on the usage. So it does not have the range of RANS models that Saturn has, for instance, for sure. And but it has a few limited examples. The key, it has always been for its usage, the fact that it has always had an excellent scaling performance, especially on blue gene Q type, on blue gene type supercomputers, but also on other supercomputers based on CPUs. Performance has always been pretty good. Over the years, we built an extensive validation set of cases. So again, this is just to, as an introduction, just to remind that in the spectral element method, essentially, the flow is discretized using Lagrange polynomials built on Gauss-Lobato-Legendre collocation points. And one of the key is the exponential convergence in polynomial order, which allows to decrease the error exponentially as the polynomial order increases. So we typically operate around polynomial order 7. That would be our sweet spot usually, especially on GPUs. And the solution strategy is basically, it depends on the type of discretization we use. There are two choices in NEC 5000. One is to use the same polynomial order for both pressure and velocity. The other is to use actually a lower order for the pressure. If the same polynomial order is used for the two, which is now the most popular choice, I would say, the time splitting scheme comes back to Tomboulides and Orszag, and it's a very robust scheme, and it essentially involves 3 separate Helmholtz solves for the velocities, or 1 Helmholtz in case you want to solve it as a couple system, and then a Poisson solve for the pressure and a correction on the velocity. So nothing very complicated there. Of course, most of the computational cost is in the pressure, and a lot of work goes into the preconditioning for the pressure Poisson equation, and that's where a lot of the work is always. And using AMG primarily on the coarse grid solve and spectral element multigrid within the element, it's possible to achieve very good scaling on blue gene type systems, which now unfortunately we don't have anymore, and it can reach up to 2,000 points per core. A decent scaling performance, and so like let's say 70% parallel efficiency at 2,000 points per MPI rank. So which is allows to go really fast in these machines. So we first had a version of NEC 5000 using OpenACC that was running on Summit and was okay. It wasn't particularly good, but we really refactored or retaught the code in recent years. Because we have to realize that in the United States, essentially the next decade will be a GPU decade when it comes to supercomputing. The current generation of supercomputers like Summit and the next for sure will be GPU-based supercomputers. If we want to run at scale, there is no other choice in the United States. If we running on Fugaku will be different, of course, but in the United States systems, we are talking about GPU systems. So NEC-RS is the next evolution of NEC 5000. RS stands for racing speed, in case you're wondering, and it's very different. It's a very different code. In many ways. In some others, it's very similar. It still uses the same time splitting scheme I just described, the Tomboulides and Orszag scheme, time splitting scheme, and it has it relies on C++ primarily, however, for a lot of the coding, and it relies on a library, on a layer of libraries where basically the key kernels are compiled at runtime. Okay, we use just-in-time compilation to maximize the performance of key kernels, which makes it sometimes a pain to run on machines, but it's maturing very fast. I am amazed at the speed of this code compared to what I've seen before. I've never seen anything running this fast, I have to say. Right now, as you're gonna see, on 100 billion grid points roughly, it can run 0.2 seconds per time steps. And it doesn't seem to have any problem with scaling whatsoever. As you can see here, these are like some tests from actually last year. The efficiency has not changed. What has changed, however, is the actual speed of the code, which has increased by a factor of 4-fold. If you compare like key operators like the matrix vector operators and check against the roofline for the GPU, these are like on Summit we have V100 GPUs. It's really like on top. So some of the key kernels are obviously performing very well. Obviously, in a Navier-Stokes solver, there is much more than one kernel, and it's important to optimize the whole thing. The key has been actually a combination of algorithmic improvements related to GPUs and other aspects. One thing we're doing right now, for instance, we are overlapping the gather scatter to the matrix vector operation, and this is improving significantly the performance. So I'm going to start talking about now some examples of what is possible to do with NECRS. But first, let me say, we do a lot of validation, but this talk is not particularly about validation. Okay, so but let's keep this in mind. We do a lot of it, and more and more we're going to transition that to NECRS. One thing that is good is that all the cases that can run in NEC 5000 can run in NECRS. So we are porting a lot of the validation base to NECRS. And the other thing I want to mention is that we don't sit in a vacuum. Actually, we have an active collaboration with NRC, and NRC has selected these codes here for the analysis of advanced reactors. This is the Blue Crab suite, and you can see that when it comes to CFD, we are involved in that particular environment, and this thanks to the MOOS interface. So now I'm going to give two examples of things that NECRS allow us to scale up. One is typical pin bundles, and then the other is pebble beds. So for pin bundles, okay, so I'm going to start for what we have done already. So we have done, this is a published paper from 2019. This is a Journal of Heat Transfer, and it just shows a DNS of two subchannels, okay? At Reynolds number of 22,000. This was designed really to, we estimated the Kolmogorov length scale and then design a very fine mesh. The mesh you see here, actually, these are just the elements. Then there will be the Gauss-Lobato points within each element. So this is like a pretty fine mesh, and this was run actually with NEC 5000 on Mira, and it was sort of like reaching the limit of what is possible on Mira. When you start reaching like a few billion grid points, like actually on Mira you could easily reach 10 billion or something, but I mean we are not that far from the maximum that could be done on that machine. And so these are like some comparisons. Like this is a fairly old experiment, as you can see here, from 1983. Obviously, there are some differences with the experiment, but pretty good comparisons. In particular, it's very interesting to notice in this experiment, which has a very tight lattice, is that the TKE, in the center of the domain, you are in the center of the narrow gap, you have very high TKE compared to the wide gap. And this is typical of this tight lattice configuration where you can have very significant lateral flow pulsations between the two. And this is very well-known phenomenon. And it clearly manifests with the sinusoidal shape and very high TKE numbers inside the channel. Okay, the narrow gap. In fact, the narrow gap will have higher TKE than the wide gap, which is counterintuitive because the local Reynolds number is much higher in the wide gap region. Nothing new here so far. Interesting bit that we did in this paper was actually we looked at the turbulent budgets, which was the first time I think was in a detailed look here for that. And one interesting bit that you can see is that while in the wide gap you have profiles that are very close to channel flow, when you start looking closely in the narrow gap, you can see that production is not actually the most positive value. Okay, in fact, production is very low. The main value at the center of the domain is actually the transport term, which is an indication that a lot of the turbulence is being transported here and not produced locally. Okay, which is again an indication of strong turbulent structures in the region. So the other bit that we did as part of that paper was also look at different Prandtl numbers and so the same flow field. Okay, one of the nice things we could do with NEC is that we can run multiple temperatures at different Prandtl numbers and look at the effect of the Prandtl number over the mixing. And you can see here that obviously as you start decreasing to sodium level Prandtl numbers, you have very different profiles and frequencies that are involved. So now transitioning to what is possible nowadays. So we are extending now, we have done, this is in collaboration actually with Sofiane Behamadouche at EDF. And this is an 5x5 row bundle. And we are doing a DNS here. The summary, the preliminary results published in the literature. But we are combining here a fairly large subchannel, a very large P over D here with a fairly narrow gap here, okay? So you can see here now an anisotropy map using a barycentric map following Iaccarino. And what you have here is that the blue represents isotropy, the red represents two-component behavior, and the green represents axisymmetric. So essentially you have, so this is a fully asymmetric. So one component behavior, you have two component behavior on this side of the triangle, okay? So this is essentially a fancy variant of the Lumley triangle, if you wish, okay? But instead of having lines, you can color the condition locally of your flow field, okay? This allows to really show the differences in anisotropy in different parts of the domain. You can clearly see that the edge channels are very different patterns of anisotropy, and in the narrow gaps, you are in the edge channels, you actually have essentially two-component behavior, which is consistent with the fact that in this narrow gap, we sort of expect these coherent structures that lead to flow pulsations to develop. And in fact, it's clearly visible, okay? In fact, if we look at this, let's look here at the budgets now in the center channel, okay? With the narrow gap, in the center channels, the narrow gap, you can clearly see the production is the dominant term, okay? And turbulent transport is smaller, and like again, it's a balance of dissipation and production as typical in wall-bounded flows. But if you look at the profiles in the edge channels, again, you see the dominance of turbulent transport, okay, in the edge channels. So, and again, this points to the presence of these coherent instructions, which you can see again from the sinusoidal patterns as well. I'm not going to show it here, but you can also see them from all sorts of other things, including two-component so autocorrelation or two-point correlations. Like you can clearly see them in these classical metrics as well. now a little bit more interesting is let's add a Timble to the problem, okay? A Timble in the middle here. And again, the Timble induces the same effect, okay? So let's see here. Okay, so you have this anisotropy map here for the 5x5. Now look at the 5x5 with Timble. And again, you can see the switch to component behavior in the narrow gaps. And note that there's also some asymmetric, it's harder to reach statistical convergence in this case with the Timble. There's some, the area around the Timble becomes highly unstable when it comes to this flow structure. So this is some recent results. I mean, there's more, we're gonna publish more on this, but I thought it would be interesting to see some of this more involved little turbulence examinations that we have done recently. So the previous one I should mention, this was a DNS. This one on the Timble was more an LES. We are doing the DNS right now. Expanding to larger domains, we have also performed a 17 by 17 LES, and these are relatively low Reynolds number, but we are expanding. So we have tested it up to 175 million and 100 billion grid points, and on NECRS, this runs like fairly well as a weak scaling study at 8,000 elements per GPU. One thing about the GPU computing is that they tend to behave. GPUs are not very good for strong scaling, although I'm starting to reevaluate that notion. In general, you want to keep the number of degrees of freedom per GPU fixed and just increase the number of GPUs. So they're very good for weak scaling. Not so good for strong scaling. However, we are discovering that as we improve the performance of NECRS, we are finding a region of strong scaling for the code where between 8,000 GPUs and perhaps between I don't know, 6,000 to 12,000 elements per GPU are actually being, can be used for reasonable performance. So, and the weak and the strong scaling can be decent in this range of performance. Okay, so it's the speed up. This is actually a whole number, 11x. We haven't even tested right now because we are 4 times faster than before, so I'm not 100% sure. But we are faster on the CPU, so we need to double check this number. But it's very close to almost theoretical speed up on the CPUs. But we are also faster on the CPU. So now we're both faster on CPUs and GPUs right now. So this number probably is pretty close. So this is an example of what we're doing right. So these are 39 assemblies. It's basically the core of NewScale. And we are running some initial full core calculations here. This is a number I just got the other day, a recent update. Like we are of the order of 0.15, 0.35 seconds per time steps. And this runs from about half of Summit, okay? And 150 million elements. So the case I showed here was like just increasing the length of the single assembly, okay? We just increased it and just did a weak scaling like that. Now what we're doing, we're actually looking at a full core size pin by pin and examining the effects. And so obviously it's going to take time to get to statistical convergence. You should see these results only as preliminary, okay? But it gives an idea of what is possible now. We're also running it with RANs. Again, this is using the k-tau model, novel functions and y+1 at the wall, and using a in-link condition that is interesting. But we are aiming to do full height RANs on these calculations. And again, this is going to be 150 million elements on roughly 100 billion grid points. This is actually I ran also in the last week or so with a recent update. What we plan to do to overlay on top of the RANs is to add some momentum sources to account for the grids for these RANS models. We'll also plan to add the grids at a later stage on part of the assembly. On some of the assemblies, because obviously to do all of them will be a very expensive exercise, but to add them as momentum sources using some precursor LES. This is some grid, like full grid simulations that we have done with NEC, includes everything, including the dimples, springs, and all these sorts of effects. And the idea is then we will extract some forces that we can load. We already actually tested this. It works relatively well, at least far away from, like not in the very first diameter, but in the wake, it works pretty well. And we'll add this in the full core simulation. We'll have something to report there soon. The other item we are really excited about is pebble beds. We have done some DNS of pebble beds before, and I'll refer you to this paper. This is some these are not big calculations, so less than 1 billion grid points, but there was some, we make sure that the size of the domain was below Kolmogorov scales, and the size of the mesh was below Kolmogorov scales, and then we examined again a domain with inlet outlet and some some EAT as well. So these are like some comparison with the experiments. Obviously, these are very difficult geometries to handle. The profiles we're obtaining, we match index of refraction. There is a pretty good qualitative comparison, also good quantitative up to a certain limit. It's very difficult to control exactly the location of the pebbles in the experiment. So we consider it a successful validation, but it's a very difficult geometry to validate. The interesting bit was here that we uncover regions of negative production, which is not unexpected, because what you have here, you have accelerations and decelerations that develop in the domain. And of course, in acceleration, negative productions are not unusual. What you can also see, you can correlate the pattern of negative and positive production to the anisotropy production, because in the wake of the acceleration where turbulence is killed, you have also a deceleration where turbulence is produced. And when turbulence is produced, it's usually produced in an anisotropy pattern. So you end up with like fairly strong 1D turbulence wakes in the wake of the deceleration regions, the acceleration regions. So this was like an interesting discovery there, but what is possible now? So now, that calculation that I showed you before was last year. It was 147 pebbles. We are doing already 10,000 right now with NECRS, and we're not even using 140 nodes of Summit. We also updated the way we are generating the meshes, because this mesh now is fully hexahedral, and it uses Voronoi cell concept to generate the mesh. And you can see here, we estimate we'll be able to do the full core with 80% of Summit. And a full core pebble bed is 300,000 pebbles. So we're doing 10,000. We are already running. Now the only limit is the meshing, because meshing these things is a true pain. But we are able to mesh 44,000, and the plan now is to switch to 300,000 soon. But I'm hoping by the next year we're going to have 300,000 pebbles to show. And these are for gas reactors, of course. So I think I'm closing to my time. Sorry for taking so long. I just wanted to show that we are also working with Fraser Nash and on FIV. And the idea here is we are collaborating on the NEA benchmark that is right now on FIV. And we can run couple NEC5000 to Diablo, which is our structural mechanics code, and we are simulating the benchmark right now, and we are collaborating. We are meeting with Graham every month or so to examine how this is going, and this is just some preliminary simulations of flow past 2 cylinders. These didn't take very long to run. These are much smaller than previous calculations, just to show some of the results for this simulation. And with that, okay, I'm just gonna close my talk. Thank you for paying attention, and I'm available for any question.
Many thanks for this wide-ranging and extremely interesting presentation. Any quick questions before we move on to our next item?
Yeah, hi Hector. I'd like to ask a quick question. How long are these sort of simulations taking typically?
Which one you want to? Okay, so
something like either the Pebble or
right.
Moving towards the fuller systems.
Let's see if I can go back to the. Okay, so it depends what you mean by. So obviously this calculation doesn't take very long. Okay, it depends by the flow through time, right? I mean, at the end, one of the metrics is the flow through time and to reach statistical convergence. So these ones can take quite a bit of time, but they are not like geological timescales like some other simulations, because it can take time because you need to reach statistical convergence, and some of these pebbles tend to have very unusual statistical behavior, but we found that if using ensemble averaging, we can accelerate that a little bit. Once you start talking about taller pebbles, okay, the taller the pebble is, the longer it will take to reach statistical convergence. As a rule of thumb, it's going to depend. For these ones, they are full height, so they are very expensive. It takes a long time to especially when you start throwing in the heat transfer, it takes a long time. So it's going to take a while before we get to the point where we can use this as a production run. But I think it's important when it comes to shorter sections, they can be used right now. So it depends what you're after. That's my answer to your question. If you're after like just an examination of the radial distribution, this is something that can be done now, and it can even be a few spans of a spacer grid. When you're talking about 5 to 8 spacer grids, it takes time to converge. It's going to take a while to get to the point where we can use this as a production run. But obviously we moved significantly past recent limits.
Yeah.
Hector, do we have time for another question?
Okay. Hector, I have a question. Good morning, all. This is Ali Terani from ONR. My question relates to, thank you for the presentation. It's a very helpful and indicative of the work that has been done at the national level. In terms of for a PWR, which is of the main interest in UK at the moment, in terms of industrialization of these codes, what timescales are we looking at in terms of some of these techniques becoming available for industrial use, even to represent a quarter of a core rather than the full coverage of the field region?
So, first of all, this is an open source code. So if you want to use it, you can use it. It's fully available right now. But I think that is going to, so if you talk about doing a PWR at effective, like at quarter core, prototypical Reynolds number with all the spacer grids simulated one by one, I think that's still quite a bit away. Although I think on exascale systems, we're going to go pretty close to do that. actually, in fact, I think perhaps not the prototypical Reynolds number, but at reduced Reynolds number, we're going to go pretty close to do that. If you wanted to do today, what you could do a quarter core with some kind of momentum source and RANs. You could do it now.
Okay.
You could do it now.
Shushank, one last question, and then we could move on.
All right. Again, thank you, Elia. That was really interesting, fascinating to see your progress. My question is about the effect of strong protease, which is something we've been looking at quite a lot. We were wondering whether when the protease change strongly with temperature, where almost like the compressibility start to show in the real physics. So do you actually have different solver or different treatment for situations like that?
So yes, so NEC 4000 has had a low max solver that accounts for thermal divergence for a long time. And NEC-RS also has the low max solver in it. I have no experience with it though, so I cannot vouch for it. One thing I should say, the NEC-RS is also a fairly, I have a lot of experience with it when it comes to NEC 4000, but not in NEC-RS. So I've used it many, many times in NEC 4000, but not in NEC-RS. So I don't know exactly how well it behaves, so don't take my word for it. Also, I should also say that NEC-RS is fairly young code. So it's going to take a while I mean, it's not as robust, and you end up with problems. So I wouldn't necessarily recommend people in industry to use it straight and expect to be working right off the bat. But if you're interested in trying these methods, they are available. So I see a question from Stefano. Shushan, you saw it? It's on the chat. I'm gonna answer it. So we are not using OpenACC for NEC-RS. We are not using that, and there are very strong limitations to OpenACC. It's very hard to move it. In any case, let me say the scaling. So what I'm showing here is primarily with scaling. When it comes to strong scaling, there are limitations also to NEC-RS. Let's be clear on that, okay? Although there is some, we are now able to strong scale a little bit, but there are limitations on GPUs on how much you can strong scale. It's what it is. So regarding the computing standard for NEC-RS, so we use like a library called Oka that essentially generates CUDA at runtime, as I mentioned. So if you install NEC-RS on your computer, you will actually not compile completely the code. Each time you run the case, you will use a just-in-time compilation paradigm and essentially compile a runtime key kernels to optimize them for the particular machine you run on and the particular GPU you run on. So it's very, very different from OpenACC. Does it answer your question, Stefano? Okay, good.
Okay, so thanks very much, everyone. We're running about 10 minutes later than scheduled. So I suggest any more questions we can postpone for the general discussion session. According to our schedule, now we should take a 10-minute break. So I suggest we maybe take the opportunity to have a break now and resume again in 10 minutes time, which according to my watch will be 11:10, when then control of the meeting will be handed over to Wei.
Right, okay.